Bridge, memory, flops, and why training feels expensive. When engineers say training a language model is expensive, they mean two distinct things. The model consumes vast amounts of memory, and it requires trillions of arithmetic operations. These two costs, memory and compute, are related but not identical. Understanding the distinction and the trade-offs between them is essential for grasping why training large models is difficult and how researchers optimize the process. We'll explain why these costs arise and how they interact. Let's start with memory. A language model stores several types of data. Model parameters, which are the weights learned during training. Gradients, which tell us how to update those weights. Optimizer states, which track momentum or other statistics needed for effective updates. And activations, which are intermediate values computed during the forward pass and reused during the backward pass. Each of these components consumes memory, and as models scale up, memory becomes a hard constraint. If the total memory requirement exceeds what your hardware provides, training simply cannot proceed. Consider a model with 10 billion parameters. If each parameter is stored as a 16-bit floating point number, that's 20 gigabytes for the parameters alone. Gradients, which have the same shape as parameters, add another 20 gigabytes. Optimizer states, typically stored in 32-bit precision for numerical stability, can add 40 gigabytes or more, depending on the optimizer. We haven't even accounted for activations yet, and we're already approaching 100 gigabytes. Modern GPUs have 40 to 80 gigabytes of high bandwidth memory, so fitting a 10 billion parameter model on a single GPU requires careful memory management.
Activations are particularly tricky. During the forward pass, each layer of the model computes intermediate values, hidden states, attention scores, layer normalization statistics. These activations must be stored because the backward pass needs them to compute gradients. The memory required for activations scales with batch size, sequence length, model width, and model depth. If you double the batch size, activation memory doubles. If you double the sequence length, activation memory doubles. For large models trained on long sequences with big batches, activation memory can exceed parameter memory by a wide margin. Why not just discard activations and recompute them during the backward pass? This is possible, and it's called activation checkpointing or gradient checkpointing. The trade-off is compute for memory. By recomputing activations, we save memory but spend additional flops. If we checkpoint every layer, we reduce memory significantly, but roughly double compute. If we checkpoint only some layers, we balance memory savings against compute overhead. Choosing where to place checkpoints is an engineering decision, guided by hardware constraints and training speed requirements. Now let's turn to compute. We've discussed counting flops in previous lectures, but here we focus on why compute is expensive in practice, not just in theory. The dominant cost is matrix multiplication, but not all matrix multiplications are equally efficient. During training, we process batches of sequences, performing large matrix multiplies that fully utilize GPU tensor cores. During inference, especially autoregressive generation, we process one token at a time, performing many small matrix vector products. These smaller operations are memory-bound rather than compute-bound. The hardware spends more time waiting for data than performing arithmetic. This distinction between compute-bound and memory-bound operations is crucial. A compute-bound operation achieves high hardware utilization because the arithmetic circuits are busy. A memory-bound operation achieves low utilization because the circuits sit idle waiting for data. GPUs are designed to excel at compute-bound workloads, so memory-bound operations waste their potential. Inference is often memory-bound, which is why serving large language models at scale requires specialized infrastructure. The hardware has the theoretical capability to perform trillions of flops per second, but memory bandwidth limits how much of that capability can be realized. The ratio of computation to data movement is called arithmetic intensity. High arithmetic intensity means lots of compute per byte moved, which is good for GPU utilization. Low arithmetic intensity means little compute per byte moved, which is bad. Large matrix multiplications have high arithmetic intensity. We load matrices once and perform many operations on them. Element-wise operations like addition or ReLU have low arithmetic intensity. We load data, perform one operation, and write it back. Optimizing neural networks for hardware means increasing arithmetic intensity wherever possible. One tool for visualizing this is the roofline model. The roofline plot shows achievable performance on the vertical axis and arithmetic intensity on the horizontal axis. The plot has two regimes: a sloped region where performance scales with arithmetic intensity, limited by memory bandwidth, and a flat region where performance is capped by peak compute. Operations with low arithmetic intensity land in the memory-bound region. Operations with high arithmetic intensity reach the compute-bound region. The goal is to push operations into the compute-bound regime by increasing arithmetic intensity or improving memory bandwidth.
Let's make this concrete with transformer inference. When generating text, the model produces one token at a time. For each new token, we must multiply the current hidden state by every weight matrix in the model. Each multiplication is a matrix vector product. A large matrix times a small vector yields a small vector. The cost is dominated by loading the matrix from memory, not by the arithmetic. If the model has 10 billion parameters and we generate 100 tokens, we load those 10 billion parameters from memory 100 times. This memory traffic is the bottleneck. Training is different because we process entire batches of sequences at once. Instead of matrix vector products, we perform matrix-matrix products. Loading the weight matrices is amortized over many examples, increasing arithmetic intensity. This is why training achieves higher hardware utilization than inference, despite using the same model. The lesson is that operation efficiency depends not just on the model architecture, but on how it's used. Another memory cost arises from optimizer states. Simple gradient descent requires storing only parameters and gradients, but modern optimizers like Atom store additional state. Atom tracks both the first moment, the running average of gradients, and the second moment, the running average of squared gradients. This doubles or triples the memory required per parameter. For a 10 billion parameter model, optimizer states can consume 60 gigabytes or more. This is necessary for training stability, but it limits the size of models we can fit in memory. One strategy to reduce memory usage is gradient accumulation. Instead of processing a large batch all at once, we split it into smaller microbatches. We compute gradients for each microbatch separately, accumulate them, and then perform a single optimizer step. This reduces activation memory proportionally to the number of microbatches at the cost of slightly lower hardware utilization. Gradient accumulation is essential for training large models on GPUs with limited memory.
Another strategy is mixed precision training. By storing activations and performing most operations in 16-bit precision, we halve memory usage and double compute throughput. Parameters and optimizer states remain in 32-bit precision for numerical stability, but the activations, which dominate memory during training, are compressed. This technique is now standard in large-scale training. The trade-off is careful implementation to avoid numerical issues, but the benefits are substantial. The paired lecture will walk through the arithmetic of inference and training compute, derive the memory requirements for activations, and explain techniques like gradient accumulation and activation checkpointing in detail. To follow effectively, keep these mental models in mind. Memory costs come from parameters, gradients, optimizer states, and activations. Compute costs come from matrix multiplications, which dominate training but are less efficient during inference. The distinction between compute-bound and memory-bound operations determines hardware efficiency, and trade-offs between memory and compute shape system design. Why does this matter beyond the mechanics? Because memory and compute constraints determine the frontier of what's possible. Every year, hardware improves, but model sizes grow faster. Researchers constantly push against memory limits, inventing new techniques to fit larger models or train them faster. Understanding these constraints means understanding why certain architectures succeed and others fail. It means appreciating the engineering ingenuity required to train models that seem impossibly large. It also means recognizing that raw parameter count is not the only measure of model cost. A 10 billion parameter model with long context windows might consume more memory and compute than a 30 billion parameter model with short contexts. The shapes of the tensors, the sequence lengths, the batch sizes, and the hardware all interact in complex ways. Effective model design requires balancing all these factors, not just maximizing parameters.
Another implication is that inference and training have different bottlenecks. Training is compute-intensive, benefiting from large batches and long sequences that increase arithmetic intensity. Inference is memory-intensive, suffering from small batch sizes and sequential generation that decrease arithmetic intensity. This means optimizations that help training might not help inference, and vice versa. A model architecture that's efficient to train might be slow to serve, and a model optimized for serving might be expensive to train. Engineers must consider both phases. The rise of mixed precision training illustrates this trade-off. Using 16-bit floats reduces memory and increases speed, but it introduces risks of numerical instability. Certain operations, like softmax or layer normalization, can produce infinities or nans in low precision. The solution is selective use of 32-bit precision for sensitive operations, combined with loss scaling to prevent gradient underflow. These techniques are now mature, but they required years of experimentation and careful analysis of numerical behavior. The paired lecture will explain these techniques, and your task is to understand not just the mechanics, but the reasoning behind them. As you listen to the paired lecture, notice how each technical detail reflects a resource constraint. When activation memory is calculated, think about how sequence length and batch size were chosen. When gradient checkpointing is explained, think about the memory compute trade-off and where checkpoints should be placed. When arithmetic intensity is discussed, think about which operations are memory-bound and how that affects hardware utilization. The paired lecture provides the formulas. This understanding provides the context for why those formulas matter.
Training large language models is expensive because we're pushing against fundamental limits: the speed of memory, the throughput of arithmetic units, and the capacity of storage. Every technique discussed in the paired lecture, from gradient accumulation to mixed precision, is a response to these limits. Understanding the limits means understanding why the techniques exist and when to apply them. This is the discipline of systems engineering applied to machine learning. In summary, we've established why memory matters,
how activations dominate memory usage, what the distinction between compute-bound and memory-bound means, and why trade-offs between memory and compute shape training. The next lecture will give you the quantitative details and optimization techniques. Listen for the connections between abstract resource constraints and concrete engineering decisions, and you'll come away not just with formulas and techniques, but with an intuition for the economics of training large models.